when I was a graduate working at Ove Arup and Partners in Ted Happold's group. And this project came into the office. It's the Martihalle in Mannheim. The main architect was Muschler and Partners, but the consultant architect for the roof was Otto. And I don't know if you heard of Otto.
Mm-hmm.
Quite a few nods. Okay. I'll talk a bit more about Fry as the lecture goes ahead, but this is how I got into it. This project, the Martihalle in Mannheim, was built for a garden show in 1974. It was originally designed to be a temporary building with a 20-year life, but it's still there, and it's a listed building. There are a few problems with it now because it's way beyond its design life. It's a timber building, which of course is very relevant to Wen-Shao, and I'll show you some more details as we go ahead. Now, if you want to know how a structure like a grid shell works, then you need to go no further than getting hold of a kitchen sieve. And the reason for that is that the grid shell is made from two sets of intersecting members, and I'll show you some more details of the timber connections and so on later on. So there's two sets of laths which start off crossing at right angles, and then as the roof was lifted into place, most of those squares will deform to diamond shapes. It was lifted using scaffold towers, and in the far distance in this photograph you can just see the scaffold towers with sort of crosses on the top which spread the load out into the roof. Now a sieve like this one is made from a woven wire mesh, and what you could do is you could take a sieve like this and you could load it, for example, with bags of sugar or something like that, and see how much load it would take before it collapses, and from that you could then predict how much load a structure like this would take to collapse. For some reason, not many people seem to know about the scaling laws for models, but they are relatively straightforward, and we could talk about that more later if you're interested. This is how a grid shell behaves. Next time you have a sieve, it'd be nice to just sort of press it and see the way in which it moves as you load it, which is quite unexpected. Back to Mannheim. This is a photograph showing the structure being load tested. Those dustbins are full of water and they're hanging from the roof with wires which you probably can't see in the photograph. So the German authorities were understandably a little bit nervous about this structure because it's very, very slender. It spans about 60 meters, and the structure, let's go forward a bit, where is it here, is this. It's, as I said, timber. There's two layers of timber in each direction, and those timbers are 5 centimeters square. So the structural depth of the roof is something like that, and it spans 60 meters, and it's made of timber. Now, the form of the building, the shape of the building, was determined from this hanging model, and the idea is that this is a hanging chain model, purely in tension, and if you turn that upside down, you then end up with a structure which is purely in compression. Now, because it's a lightweight structure, you could argue that it's not necessarily appropriate to optimize it for its own weight, because you have other loads like snow loads and wind loads and so on. But the thing is that it's made from timber, and timber creeps. In other words, when you load timber, it continually deforms with time. And that means that with timber, you're more concerned than you would normally be with the own weight of the structure, with the dead load, because that's the load that's there all the time. Whereas the snow is there for a few days or a few weeks at most. So it does make sense, particularly for a timber structure, to optimize it for own weight. Whereas if you're doing the same thing, a lightweight structure in steel, that doesn't necessarily apply so much. Now, this is another hanging model. This, I think, is a reconstruction by Friotto's team of the model made by Gaudi for the Colonia Güell near Barcelona. Timber, of course, sorry, not timber, masonry, of course, is very heavy. So with masonry, it does make sense to optimize your structure for the own weight. And of course, it makes sense to actually have masonry structures being heavy, because then the weight of the structure pre-stresses the structure, meaning that it can then carry all its loads in compression. So the idea of the hanging chain, or the hanging model, it was not new, and of course it even predates Gaudi, in the sense that people like Hooke and so on were aware of the fact that if you have a hanging chain and you invert it, then you get the optimum shape for an arch, but of course not necessarily for a shell. I should say, perhaps at this stage, that even though Friotto in his atelier, which is separate from the IL, spent a tremendous amount of time building this model, in fact the model was recreated in the computer by Linkvitz, and the building was actually built from the computer model rather than from the physical model. And I think this is the last time that I know of that a highly accurate and expensive physical model was used to define the shape, or if you like, define the form of a building. That's not to say that physical models are no longer appropriate. Physical models are still very, very useful, but they're much more sketch models, and you make a sketch model from bits of cardboard, bits of wire or something, and you get approximate initial information from it, and then you use the computer for more accurate information. And of course, for fabrication, you need highly accurate information, and in the case of a steel structure, it would be information to the nearest couple of millimeters or so, which is almost impossible to get by measuring a small scale model, where if it's 1 to 100, a millimeter becomes 100th of a millimeter. You can't measure to that sort of accuracy. So here's a few more pictures. On the top left, you can see that the timber laths, which are laid out flat before being lifted up into place on those scaffold towers. The reason for having these long continuous members is that in timber it's very, very difficult to make connections between timber members which will carry anything like the full capacity of the timber. And therefore, if you want to make a grid shell from timber, the thing to do is to have long continuous members which you bend into shape. There have been some timber grid shells with distinct individual members which are joined at the nodes, but the connections for those are incredibly complicated and expensive, and have a large amount of steel in them with bolts and things. So in Portcullis House, for example, by Hopkins, which are the offices for the Houses of Parliament, there's a grid shell in there which you can't see, which you can't go in, but it's got timber members, individual timber members, and there's massive connections between each member. Just go back to here again. I don't think in this particular image we can see a finger joint, but the finger joints in timber are, as the name describes, you put the timber through a machine and it makes fingers, and then you can glue them together, and so you can make effectively infinitely long timber members. And you can do that on site. You don't necessarily have to do it in the workshop and then take it to site in a lorry. You can do it on site and make effectively infinitely long bits of wood that way. The bottom two pictures show the model that we made from Perspex in the Arup office in Soho, and it was from this model and a previous model that were the main ways in which we established how much load the structure could take, or what we had to do to make the structure stand up. As I say, there are relatively simple rules which enable you to scale the results of a test, say such as this one, up to the full scale. In the simplest case is when the model is effectively a perfect scale model of the full scale structure using the same materials. So if we made a timber model with the size of the timbers to scale and the spacing of the timbers to scale and everything else to scale, then what you have to do is apply the same load per square metre to the model as to the full scale structure. So that scaling rule is because things like Young's modulus and the strength of the timber and so on, they all have the units of force per unit area, and the load on the structure would be expressed in load per unit area as well. So that means that, well, the real structure was actually designed for, well, one of the shells was 35 kilograms per square metre, the other was 60 kilograms per square metre. The lower value was because the idea was to turn the heating on to melt the snow. And that was this particular shell, the larger shell. So that means that if we'd made the model from timber to scale, then we'd have to put 35 kilograms per square metre on the model, which I suppose, well, that's half your body weight, probably, roughly. It's quite a lot. We also did a computer analysis on a machine like this one, the CDC 6600, which in those days cost about $7 million, which is about $40 or $50 million today, and is much less powerful than a mobile phone. So we had to do the analysis on an exceptionally coarse grid. I think it was a 5-meter grid, because we couldn't model every single node. That would have been far too many. Whereas you could model every single node on a mobile phone now. We also built a model to model the erection sequence when the structure was much more flexible. The reason it was much more flexible is these bolts here were loose when the structure was lifted up, and there's a slotted hole you can just see here. So the structure was much more flexible while it was being erected than it was in its finished state. And this is an aspect of all these actively bent, as people call them, actively bent structures, where the idea is that they're relatively flexible and you're bending them into shape. and then you make connections which allow everything to work together and then become much stiffer in the finished state.